All right, so our battery has a voltage of 24 volts, and sometimes the potential difference across the battery will be expressed as epsilon, this capital E looking thing. That just stands for electromotive force, which is what voltage has often colloquially been called in the past. So we've got plus 24 volts at our positive terminal, and I'm just arbitrarily calling the negative terminal 0. And if this part of the circuit was connected to the ground, then that would make it even more explicitly clear that this is a voltage of 0, because anything that's connected to ground is just arbitrarily given that value. So we've got a network of 3 bulbs, and we want to simplify these bulbs using the rules for resistors. So first you might make a prediction of which bulb you think is going to be brightest in this case. They're matched bulbs as far as resistance goes. So when that happens, the power that the bulbs dissipate will reflect their brightness. We've got 135 ohms for each of them. So just think about which one do you think will be brightest and why, And then we'll mathematically determine how bright each bulb is based on the power that they dissipate. Okay. Now that you have a guess, let's go through the math of simplifying the circuit to see if your guess was correct. First thing I'll do is I'll redraw the circuit in just a symbolic form here. All right. We want to see if any of these bulbs are directly in parallel or directly in series with each other, meaning it's one resistor wired to another resistor in series, or do we have a place where the resistors are wired in parallel and one side of the resistors meets and then the other side meets to complete the branch. This is a case of parallel resistors right here. Okay. It's because the current could take one of those two paths. And so one thing I didn't really stress in the past was the meaning of conventional current. So conventional current flows from positive to negative. And historically, it was just assumed that the positive charges might be the ones that moved in a circuit, but it turned out upon further inquiry that actually the electrons are the ones that move the most in the circuit. However, we still use the convention of drawing the flow of positive charge, and that would be what we call I, the current. So the current that flows out of the positive terminal would be called I1. I'm calling it that because it flows through bulb 1. But the same amount of current that leaves that positive terminal has to come into the negative terminal. So both of those sides of the battery have the same amount of current. And that's why I'm calling it I1. Okay. Now when the positive charges get to this junction, this red point here, they have to decide, will they go along the left path and get to the other side, or would they go along the right path and get to the other side? So that brings up an issue called Kirchhoff's Junction rule. What it says is that the current I1 will split into two parts. one which follows the right path through bulb 3, so we'll call that I3. And then there will be another current which flows through the bulb 2, I2. And so to write a Kirchhoff's junction rule equation, you just have to say that the sum of the currents coming in has to equal the sum of the currents leaving the junction. Okay, so the rule to write for this particular situation would be I1 equals I2 plus I3. It's a statement of conservation of charge, which means that charges can't be created out of thin air or destroyed. They have to pick a path, and they can't take both paths. Well, technically in modern physics they kind of can, but that's a little advanced. We'll get to that later. Anyways, let's use this for now as a problem-solving technique for simplifying the circuit. Okay. One of the other rules we have is Kirchhoff's loop rule. And the loop rule says that the sum of all the potential changes in a closed loop will always equal 0. Now, it's a little tough to analyze the loops right now because there's so many circuit elements involved. But if I was to just simplify it on the side to show Kirchhoff's loop rule, I'm going to show what I mean by a closed loop. When we say a closed loop, we mean starting at one particular point in the circuit and traveling all through the wires. You can only take one path, though, and then you come back to where you started. That's a loop. I'll call it loop 1. Okay. Now, the idea is that if you study the potential changes around the circuit, they have to add to 0. So you're going to start off at 0. You add 24 volts when you go through that battery the right way. The right way being from negative to positive, because we're talking about conventional current. So that'll be a plus 24 once we get beyond that. And there's a resistor here and a resistor there. We're going to have to lose a total of 24 volts in those two resistors. Now, I don't know the proportion yet of where we lose the voltage the most, or how many volts is lost in each resistor, but they have to add to 0. Or, the whole thing has to add to 0. All right, not only that, but we can make another loop as well. We can go, better redraw it. We can go along the outside loop. By that I mean starting here, going all the way around, taking the right path this time, and coming back to the battery. That could be called loop 2. And Kirchhoff's loop rule has to hold for both of these situations. So now let's use the techniques of circuit simplification to see if we can discover what those voltage drops are. Okay, so take our original circuit. First I'll draw the original. Okay, now I'll draw a simplified version of it. I combine the two parallel resistors into one. Okay, now this one is, I'm going to call R3, this one's R2, this can be R1. That would make this one called R23 because it's a combination of the parallel resistors 2 and 3. And this one just stays R1. And then finally, we can simplify the whole thing down into just one resistor for the whole circuit, which we'll call REQ. All right, so what rules did I use? These guys were in parallel. Okay, so we want to use the rule for parallel. The rule for parallel, though, is that weird rule. 1 over R2 plus 1 over R3. Okay? However, when we do these guys together, we see that they are actually in series. So the rule we'll use there is the rule for series. And when it comes to resistors, we just add them. So that's going to be R1 plus R23. Let's plug in the numbers. Each of them was 135 ohms. So we'll do 1 over 35 plus 1 over 135. I'm getting 67.5, which is half of the resistance of them individually. So the idea being that opening two channels where current can flow actually will end up allowing more current to flow because the overall resistance of that parallel branch is less than just one of the resistors alone. So 67.5 ohms is what we're talking about. R1 remains at 135, of course. And now we just want to add them together. 135 plus 67.5. That'll be our equivalent resistance. It's 202.5. Okay. All right, now our job is going to be to find these currents, and that'll allow us to finally answer the question of what is the current through bulb 1, what is the current through bulb 2. We know that we've got 24 volts across our equivalent resistor here. So we just want to zoom in on it and use Ohm's law on it. According to Ohm's law, I1 equals delta V over R EQ. Remember, I1 is the current flowing through the whole circuit, and it's also the current flowing through the battery. So if we divide 24 volts by 202.5 ohms, then we'll discover I1. It's 0.119 amps. All right, so just for a second, I'm going to go back here to my original drawing. Now we know there's 0.119 amps coming into our junction here. It's going to split into two currents. So you may be able to already guess what currents I2 and I3 will be based on the symmetry of the situation. like it's going to be half. It's going to be half of I1 in the left branch and half of it in the right branch. All right, but we can work our way backwards to prove that. And we also want to find the voltages across the independent different resistors here. So let's apply Ohm's law to each of them individually now. I'll do the first resistor first. Okay, so Ohm's law will say delta V of the first bulb will equal the current going through that bulb times the resistance of that bulb. That's just applying it to bulb 1 alone. And we don't know the voltage drop of that bulb yet. But now we can find it, because we have the current and the resistance. It's 16 volts. All right. Now, we can actually use Kirchhoff's loop rule to determine what the drop must be in the other resistor then. Okay, if we lose 16 volts in that first resistor, and we know that we've got 24 volts total that need to be lost in the whole loop, then how much gets lost in that second resistor? Well, it would be eight volts. We lose more potential in that first resistor because overall it really does have more total resistance than the combination of the other two, right? You got the same current, more resistance, you're going to have more potential dropped in that bulb. All right, so now we can go back and just start to fill some of these things in. It's a 16 volt drop here. According to the loop law now, what is the voltage drop in bulb 2 and 3? Well, let's check it out. You have 16 volts lost in this resistor. In any one loop, you have to lose it all, right? So how much voltage is lost in R2? It has to lose 8 volts. There's no other way it could be, because there's no way that we could get back to 0. And then check out loop 2. You lose 16 volts in this resistor. You have to lose a total of 24 in any loop. So you have to lose 8 there as well. So this just shows that parallel resistors will both drop the same voltage. So this is 8 volts, and this is 8 volts. All right, now let's apply Ohm's law to just one of these resistors now. Okay. So we'll do delta V for number 2 will equal the current through 2 times the resistance of 2. We know we're going to lose 8 volts. It's 135 ohms. So I2 must be okay, there we go. 0.059 amps. All right, so we got 0.059 amps here. Obviously, if we do the same calculation for this guy, we're going to get the same thing because it has the same voltage drop. So we're going to have 0.059 amps there. And remember, we had 0.119 amps coming through. So it looks like Kirchhoff's junction rule here will hold. The 0.119 amps, it splits in half, and half of that is 0.059 amps apparently. All right, so that's going to be our answers for this. 0.12 amps for bulb 1, 0.06 amps for bulb 2. All right, so which bulb is brightest here? Well, if you recall from last time, the power is determined by multiplying the current through the bulb times the potential difference of that bulb. So for our first bulb, it ends up being 0.119 amps times 16 volts, 1.9 watts. Okay, now we want to find the power of the other bulbs. So we'll just do I2 times delta V2. The current here was 0.059 amps. Delta V turned out to be 8 volts. And it's 0.47 watts. So each of these is 0.047 watts. So if you predicted that bulb 1 would be the brightest, then you were correct. The reason why it's the brightest is because all the charges that go through bulb 2 and 3, they have to pass through bulb 1. There's no way they can get to bulb 2 and 3 without passing through bulb 1 first.